Gostaria de convidar então o Dr. Evert Lataire, yeah. Nautical bottom, how to keep ship under control. Thank you.
Thank you, and good morning. I would like to show you the influence the mud has on the ship. And I'm from Ghent University, but we have a very close cooperation with Flanders Hydraulics Research, which is the affiliation of Joris, the previous speaker. This is an overview of my presentation, and let's start with the introduction. So, as shown before, this is what happens. First of all, the dredging companies in, for example, the harbor of Zeebrugge start to complain that they were no longer dredging solid mass or material, but they were dredging water, and they don't earn money with dredging water. Second, the survey techniques were not adequate. They depended on how the survey was done, and this is such a result of the survey, and it depended whether the measurement was done at 210 or 33 kilohertz. So what we see exactly here is, as shown before, this is the top of the mud layer, and this can be seen as the solid bottom. So the water, the mud, and a solid bottom. And therefore we had to make the transition from the bottom up to the nautical bottom. If the seabed is very flat, then the nautical bottom and the bottom itself are the same. And if you have boulders or if you have rocks, then it's the highest point of the highest rock, which is of importance for the ship. And if you have dunes, it's the same. It's the highest point of the dune, which is of importance. So that's what we call the nautical bottom. But this is different if we have a mud layer. Then it's too conservative if you take the upper or the interface between water and mud. But it's too dangerous to take the hard bottom. And therefore, the previous shown Piank definition of the nautical bottom was done. And for the first part, which has actually nothing to do with the ship. It's all about the mud, and therefore we need to know what kind of mud we have and what are the properties of that mud. While for the second part, the unacceptable effects on the controllability and the maneuverability is what happens with the ship if you are sailing above or very close to this mud layer. And this is what I'm talking about now. And I said before, this definition was initiated in the Piank Work Group 1397 and recently confirmed by the Piank Work Group 49, which is for the horizontal and vertical dimensions of harbors. I would like to give you some overview of the research we have done in the past. In the early 80s, when the first area of interest was the harbor of Zeebrugge, the harbor which suffered from a lot of mud into the harbor, and therefore both sedimentologic studies, so we have been investigating the mud itself, have been done as some minor nautical studies. Therefore, in the late 80s, we have towed in a flume actually ship models above natural mud. So we took mud from the harbor of Zeebrugge, put it in a flume, water on top of it, and then towed a ship model above this water and mud. While a few years later we did the same with self-propelled models, but no longer with natural mud, but with artificial mud. And this is to control better the properties of the mud, so which can be controlled like density and viscosity and so on. This was also done 10 years before in the Netherlands the same way with the same artificial mud. Then we jump to 2002 to 2004, and then we have done a very, very extensive model tests or systematic tests, and therefore we have a little bit abused our towing tank, and we've split our towing tank into 3 sections. A section for the water, the contaminated water, or to store the contaminated water, a section to store our artificial mud, and the real test section where we carried out our model tests. And this systematic series consists of more than 20,000 captive maneuvering model tests. This could only be done because our towing tank or our carriage is fully automated and runs 24/7. And we have done tests with 3 ship models, 2 container vessels and 1 tanker, the Osaka actually. And we have made different combinations of mud and water, and this should be a row and the viscosity. But anyhow, we've changed the mud properties, we've changed the thickness of the mud layer, so this thickness has been changed, and we've changed the water on top of this mud together with these ships. And this creates a combination of 80 different mud-water combinations. And like you see, we've towed the ship model through the water, above the mud, close to the mud, into the mud, and more into the mud, and this for different thicknesses of each mud layer. And also, as you can see, the orange dots indicate the type of mud, of artificial mud we have used. And we changed the density, as you can see, but we also changed the dynamic viscosity, because as shown before, it's not only the density which is of importance for a mud, but also the things like the dynamic viscosity. And these 2 dots, for example, they have almost the same density of 1.25, but their dynamic viscosity is quite different. After these model tests, we've created mathematical models. These mathematical models to simulate the forces on the ship have been implemented in the ship maneuvering simulator, and then we start the studies. First of all, again, for the same port of Zeebrugge. And after that, more worldwide interest was for this specific research, and we have done in different locations all over the world, among one in Brazil. We have done some research, or we aided some simulation studies for them. Yeah, we get some awards as well for this specific research. Now I would like to show what happens when a ship sails above this layer of mud. First of all, if there is contact between the ship and the mud, or if the keel of the ship is submerged into this layer of mud, then the properties of the mud itself are of high importance. Properties as density, but also rheologic properties, viscosity, yield stress, and the time dependency of the mud. But there's something strange as well, because it's a 2-layer system. There is not only a free surface between air and water, but there is also an interface between the water and the mud layer. And you get a wave formation, of course, between air and water, but there is also some wave formation between the mud and the water. And this one is very important if there is no contact between the ship and mud, but if the ship is sailing above the mud. This is a still of a video I would like to show you immediately, but this part is the bow section. It's like this part of the ship model. Here you can see the water, and here you can see the mud touching the window actually, and this is the layer between mud and water. So this ship model is does not touch any mud. It's above the interface water mud. I know, should hope it works. Yes. So what you see is the mud starts to move because the ship model is coming from left to right. This is the bow section of the ship above the mud layer. this was the bow thruster. You see the acceleration of the mud. But in the end, you'll see that the propeller and hull interfere now with the mud. And this is of high importance of the maneuverability of the ship model. Although at rest the ship was not touching any mud, when sailing it is. And on your left you see the same ship at 5 knots upscale and at 10 knots, and the green line here indicates the interface between water and mud. And as you see, this high wave at a higher speed is behind the vessel, which is not the case at 5 knots. And this interferes with the propeller and with the rudder, and doing so with the maneuverability of the ship. And if we lower the water level above the mud layer, almost the same happens. And this is when the ship is in the mud layer, or immediately in the mud layer, or even deeper. So this gives different wave formations between, or mud wave relations on the interface of water and mud. Now, there is some interaction between the ship and the mud, or what I've been investigating is on the behavior of the ship when sailing above the mud. This is a more recent research we have done at Delfzijl in the north of the Netherlands. And this is a track of the two echo soundings, the low and high frequency echo sounding. And what you see in the first part is that both are very close to each other. So we can expect not having any mud there. But they widen a lot. So this black line indicates the top mud layer, while this brownish line indicates the solid bottom. Here there was a mud trap. So this is a very thick layer of mud. So we have the solid bottom, a lot of mud on top of it, and above that, water. This 0% line is the position of the keel of the vessel. So as you see here, the vessel was not touching any mud. It was always sailing through the water with above a layer of mud. This black line indicates the forward speed of the vessel. Oh, this is full scale. So this is no ship model. This was all measured on full scale on the vessel. So we were measuring the forward speed, but also the propeller action. And for this period of time, there was no change at all in propeller action, but the forward speed dropped. And this drop initiates immediately when the ship sails above a layer of mud, although it was not touching any mud. And we have seen that this is not because of an increase in resistance, but a decrease in the propeller efficiency. What we see here is these are all types of different mud and thickness of mud and properties of mud. Here you can see the propeller efficiency, and this line is the same propeller efficiency when sailing above a solid bottom. So close to 0.3, an efficiency of 30% when sailing above a solid bottom, decreased to 20 and even 10%. So the efficiency of the propeller decreased. So it was no longer creating enough thrusts to pushing the ship forward. And if we look at the resistance, as long as we sail above the mud, not through the mud, but above the mud, then the resistance slightly increases, but not very significant. While when you are in the mud, when the ship is touching the mud, this resistance increased dramatically. This is a very different type. We've seen that the rudder forces can become unstable when the keel was close above or in the water-mud interface. And what we see here, the green line is how it should be. If you turn your rudder to port, then your ship turns to port, and vice versa. But what's happening that the ship turns in the wrong direction. You're giving 15 degrees of port and your ship is turning to starboard, which is very dangerous and unexpected behavior of this layer of mud. The turning circle is, you take your ship, it's a standard maneuver, and you turn around with your ship, and then you measure the diameter you need to turn your ship with a constant propeller rate, with a constant rudder angle. And in deep water, this is the diameter. And this diameter increases when you go closer to the water-mud interface, or very close to the water-mud interface. It becomes very big. But once you're in the mud, it decreases again. But remark it will take more time to make this turning circle than this, because the resistance has increased, but the turning circle itself will decrease even more. So here you could say it's better to sail in the mud than just above the mud, which is not what everybody wants to hear. In the late 80s, when the harbor of Zeebrugge was developed, there was one trip with a hopper dredger, the Vlaanderen 18, where they sailed actually in consolidated mud. So the mud was fully consolidated. They were sailing in an area where no ships were, where the port was being developed, and they were sailing at 2 knots just to test it. It was a very frightening moment, because although the boat thrusters, very powerful boat thrusters of the hopper dredger were used, and the ship was, or the propeller was fully astern, the ship did not decrease at all. It was just sliding at a constant speed of 2 knots, closer and closer to the breakwaters. And it was just in time that the captain could control its ship again, and no damage was done. But it was a very, very frightening situation. So sailing in consolidated mud is never ever a good idea. To be able to help your harbor, we have performed some simulation studies, and therefore navigation in muddy areas requires, first of all, an adapted or a new definition for your nautical bottom, which takes into account the properties of your mud. But it also needs adapted survey techniques, as we've seen in previous presentation, and together with that, adapted dredging techniques, but also a different nautical control strategy. The pilots must be aware of the mud layer, but also the measurement of the water depth they have on board of their vessel can be very frightening when they reflect on the 210 kc measurements. And this indicates also the importance of a simulation, that they feel and that they know beforehand what happens and why it is possible to sail so close or even in this layer of mud. And this is one of the first cases with container carriers to Zeebrugge. This is inbound, for example, but here we have a rather high cross current, so they need about 10 knots to enter the harbor, but of course they need some time for the speed reduction to enter the quay wall in the end. And tests have been done, simulation tests have been done with different pilots and quite a wide range of mud layers, not checked or close, of course, checked to the mud layers as in Zeebrugge, but in a wider spectrum with high densities and different dynamic viscosities. And every simulation has been done, and then first the pilots made a conclusion on whether it was possible or not to sail in this specific situation, and they marked it with different colors. But this also depends on whether they had tug assistance or enough tug assistance, or if the bollard pull or the strongness of the tugs was high enough, and so on. Afterwards, together with the pilots, we made a distinction between positions or mud layers where they could sail safely or not. This is what we came with. And this is what then the final, or at least for the moment, the final situation is in the harbor of Zeebrugge. As said before, you can penetrate with your ship 7% of your draft into the mud layer as long as you stay with 10% of your draft above the layer of 1.2 ton per square meter. This is based on dedicated simulations carried out at Flanders Hydraulics Research. Again, this has nothing to do with any other port in the world. You have to do it for each port differently. So, for the ship behavior, the dynamics of the two-layer system is of importance because this wave at the end influences both propeller and rudder, and doing so, it influences the maneuverability of your ship when sailing in or above mud. And you need the meteorology to check what kind of mud you have and what the influence is of your mud on the maneuverability of your ship and the resistance. But for the navigation, you need criteria for your nautical bottom, both for nautical charts, the pilots or all people sailing there close to this mud-water interface need to know where this interface is. But these are not the same charts the dredging companies want, because we have dedicated charts for both dredging works as for nautical charts. Then, on the other hand, if a ship wants to call the harbor of Zeebrugge, we have a dedicated admittance policy, and therefore we have to check whether it's feasible or possible for a ship to call this harbor. Therefore, we need to position relative to the nautical bottom and what the maximum penetration into the mud is. This is the 10% above 1.2 and 7% into this mud. As said before by my colleague Joris, the awareness is also of high importance, that the pilots know what's happening and why we do think it's possible or believe it's possible to sail in the conditions we gave them. And to be aware of the new behavior of the same ship, therefore we use adequate training in all dedicated ship maneuvering simulations. No, I can only thank you. Thank you.
Thank you.